Computer. Okay, now the recording is on. So, good afternoon, everybody. So, we welcome you all to take part in the seventh Gauge Gravity talk of season 2. Now, just a second. So, this is an online seminar series which focus broadly on diverse topics of gauge gravity. Now, the seminars are held roughly once a month, preferably Wednesdays. These talks we record it and we eventually post it on CHEP YouTube channel. There's an instruction for the audience. So audience, they will be muted during the talk. And if they have any questions, they can raise the hand, or like if there are urgent questions, they can immediately ask by just interrupting during the talk. And so today's speaker is Dionysios Anninos. So please pardon me if I don't pronounce this correctly. He's from King's College.
It's okay.
He did his graduation from Cornell University, followed by a PhD from Harvard under Professor Strominger. Thereafter, he was a postdoc at Stanford and Princeton, and following which he joined King's in 2018 as a faculty. So today he will talk us about his recent works on feature of the partition function for lambda greater than 0 universe. So over to you, Aninos.
Okay, thank you. And so I'm at a cafe. I'm sorry I had an internet situation at home, but I hope the connection is stable. I'll remove my video to make sure the slides are stable. Okay, so I'm very happy to be giving this talk. And the topic has to do with theories of gravity with positive value of the cosmological constant. And as we'll see, we're going to explore a particular aspect of these theories, which is the partition function. Okay, and this is work based in a growing number of excellent collaborators who I list here. And throughout the talk, I'll mention work performed in collaboration with different subgroups of these people. Yeah. Yeah, as was mentioned, if you have questions, feel free to raise your hand or ask. I'm happy to take them. So the title I felt was a little opaque, features of the partition function of the lambda positive universe. What I really mean by this title is that I would like to study things about the gravitational path integral for positive value of the cosmological constant that we still don't have a good understanding of. And by that I mean in comparison, for instance, to the analogous case of the black holes, where we have more control, not complete, but more control of the gravitational path integral. Okay. And the perspective of this talk, I think, is nicely summarized in a beautiful article of Steven Weinberg, who emphasizes that the opinion that we ought to understand our theories, what our theories entail, even when in practice its predictions cannot be verified, at least immediately experimentally. And so we will take a very precision or calculational approach to the problem and see how far we can push the calculational aspects of questions that seem reasonable for this type of theory. Okay? So we're going to study at a rather technical level the question. Does anyone see the sharing screen? Is the screen not visible? Is it visible now?
I think you have to probably share. Or is it? I can see it, but I'm not sure about the others.
It's visible. Sorry. So let me go
Yeah,
back then
now
to
it
the
seems
first
like
slide.
it is visible.
Oh, okay. Thank you. Sorry about that. So, okay. So this was just the title slide, and then this was the less opaque title. And let me show you again this paragraph of Weinberg, which I think is very, very sharply put, that I like the perspective for this problem, which is that this present work is motivated by the opinion that we ought to understand what our physical theories entail, even when in practice predictions cannot be verified experimentally. Just like field theorists in the 40s and 50s took pains to understand quantum electrodynamics to all orders and perturbation theory. even though it took a long time to start to see this effect. Okay. So the outline of the talk is as follows. I don't expect people to be experts on this lambda positive problem. In fact, no one is really an expert in this problem. And then, so I'll review the geometry and the relevant symmetries, and then we'll discuss this object, calculational object that we'll be interested in, mostly on the leading saddle, which is a sphere. And then I would like to discuss two topics that have been part of recent papers that I wrote, that I've been involved with, which is going beyond the leading saddle and studying theories with very specific particle spectra. So this is the outlook of the talk, and probably we won't have time to discuss some other models. Okay, so geometry and symmetry. So the basic stage for the talk is this spacetime over here, which is a maximally symmetric space with positive value of lambda, which is exponentially expanding toward the future, but okay, in its most complete form also toward the past. In our universe, we have mostly evidence for this portion of the spacetime in the future part. Can you see my pointer when I'm moving it? Maybe someone can put in the chat.
Yes, I can see the pointer.
You see the point. Okay, so I'll use the pointer. So we have evidence mostly of this part of the space where we are in this inflation or the current present accelerated expansion of the world. So in a sense, we are pressed to understand gravity and physics in this piece of the space, but it's sometimes useful to have a more complete chart of the idealized spacetime, and so we will discuss a more idealized version of the problem. There are many isometries, in fact, the maximum number of isometries for the space, but they are not the Poincare symmetries. Instead, they are what are known as the de Sitter isometries, which is mathematically SOD plus 1,1. And this you can view as the D plus 2-dimensional Lorentz group or the D-dimensional Euclidean conformal group, but here this is the 4-dimensional or the D plus 1-dimensional de Sitter isometry group. And although it appears in Euclidean conformal field theory, this group, here it's describing a Lorentzian spacetime. And this is an important point when it comes to questions about the unitarity of the particles and things like that. Also, notice that the space has no asymptotic null or spatial infinity. And so traditional observables that we like to study in gravity, like boundary correlation functions or an S matrix, are not available. And so we are already, by the very structure of the spacetime, we have to grapple with what kind of observables or calculables we should study in this context. And this is a question of how to organize the theory of cosmology. Of course, observables exist because we make observations inside of a cosmology, but the theory of these observables is an open problem. So in the absence of an S matrix, or more generally, nice invariant observables, and by invariant I mean under field redefinitions, diffeomorphisms, gauge transformations, whatever invariances one would like, which for instance the S matrix is, we are prompted to study other calculable or observable quantities, if the theory even permits them. And this is important, I should emphasize, because we need a way to define in such a universe, if lambda is constant or it persists, we need to have a way to define in an invariant matter what all the couplings of the effective field theory are, which is a large amount of information because you have all the couplings of R squared, R to the fourth, and so forth. So it's a very important question, I think, to understand what are the truly invariant calculable quantities in these theories. Now, another reason the question of observables is hard in cosmology is that if space is expanding sufficiently fast, it doesn't have to be exponentially fast, but sufficiently fast. Any local or quasi-local apparatus inside the space is shielded from most of the space-time by a cosmological horizon. Yeah, and so many of the observables that people like to compute, for instance, are that are anchored in the future boundary over here are really not very physical from the point of view of a quasi-local apparatus. And we have to deal with the problem in a more quasi-local way. By quasi-local, I mean physics that's larger than the Planck length, but smaller than the cosmological scale, or of the order of the cosmological scale, but not much larger. Yeah? So in this idealized world, one can express this quasi-local issue in a more clean way. In particular, the experience of an inertial world line in this space is given by what's known as the static patch metric, which is a spherically symmetric static spacetime for which there's only radial dependence. Time here, t is an isometry, time translation isometry generated by some subgroup of the de Sitter group, namely the SO1, 1 subgroup. And psi is like a radial coordinate. And note that instead of an expansion in this space, what one has is the development of a cosmological horizon at psi is equal to 0. Okay, so you have a horizon that covers the observer. And at least naively, this horizon has some similarities to black hole horizons. For instance, it has a Hawking temperature that emits a very, very small thermal radiation. Okay, so that's the quasi-local picture. And of course, on top of the space, one can populate it with matter fields. And in particular, we have the matter fields in de Sitter, and we have to find a nice way to characterize the matter fields in de Sitter. And the way to do that is through the classification of unitary reducible representations of the de Sitter group. This is in the spirit of the Wigner classification of particles in Minkowski space, but here for the de Sitter case. And these have been classified. The problem has been beautifully solved in early pioneering work of Harish Chandra. And they are labeled by some quantum numbers that are reminiscent of the conformal field theory. And in DS4, just to give you a flavor of the representations, the generic representation known as the principal series has a complex value of delta. This is a unitary representation that has a complex value for delta, but it also allows for a few real values or integers, depending on whether the particle is massive, light, or a gauge field. Now, there's many things known about these irreducible representations. For instance, the character is known, and H over here is the static patch Hamiltonian. It's the SO1, 1 generator. And what is important to emphasize is that it's a non-compact Lie group, and so this is a non-compact generator, so its spectrum is real and across the whole real line. Yes, so here's the spectral decomposition of this trace, and there's a density of states associated to each eigenvalue omega of H, the SO1, 1 subgroup. And one can also compute this integral exactly and yielding the following character expression. So here T is not time, I should say. It's more like a chemical potential. It's just a parameter that you use to express the character of the representation. And notice that it's different from the characters we're familiar with in CFT because it involves, for instance, both what we would call the conformal weight and the shadow of the conformal weight. So delta and 3 minus delta. So it's a different type of representation theory, and this is a representation theory appropriate for the de Sitter unitarity. And it has been studied throughout the years. In addition to characters, of course, the tensor products are not completely, but broadly understood. And they're because energy is not conserved in this space, tensor products can contain in their decomposition a very rich number of particles, even particles that are lighter than the two particles that you're taking the tensor product of. So one that I think is particularly interesting is that the tensor product of a spin-a-half massive particle and a photon in de Sitter yield inside of it the Hilbert space of a de Sitter gravitino, which often contrasts statements about supersymmetry and de Sitter space. Okay. And so So let me give you a little bit more flavor of the spectral density. So this rho of omega is a smooth function of omega. It has peaks, but not sharp peaks, not delta functions. So these are more like resonances. They have a width. Particles decay because they are inside of a thermal bath or a horizon. However, in the complex omega plane, this function is meromorphic and it has poles, and these poles correspond to the quasi-normal modes of the static patch, in case you're familiar with the notion of quasi-normal modes. And so this Harishchandra work actually coded a lot of beautiful physics of the static patch inside of it. I think it's nice way to express this. Okay, so let me pause now and see if there's any questions, because this was meant to be a very brief introduction to the symmetries and the space-time and the classification of matter fields in the space-time.
And Aninos, so in the previous slide, this new that I noticed, what was that?
So new, sorry,
If you go
new
back,
over here.
yeah, okay,
Yeah.
I see.
So in the principal series, this scaling weight is labeled by something like a 3/2, or in general d over 2 plus I nu, and nu is some real valued parameter. Physically, this nu is related to the mass of a particle in units of the de Sitter length scale.
I see. So there's a question by Arnab.
So
yes, one question. Could you go back to the previous slide? So when you write down the character, so it had e to the power minus delta t and then another part 3 minus delta. So does that part come from the complementary series representation, or is it still a part of the principal series?
This kind, thank you. So this structure of the character is true both for the principal series and the complementary series. However, it is not true for the a different representation, which is the discrete series, where the character takes a more complicated form.
I see.
Yeah.
And is it a feature of only t equal to 3? Sorry.
No. It's very general, this structure. And notice that even though delta is complex, here you're summing delta and its complex conjugate, because 3 minus delta is its complex conjugate. What really has to be real in the sitter is not so much delta, but the Casimir, which is equal to delta times 3 minus delta.
Okay.
So there's a lot of formulas that are invariant under delta goes to 3 minus delta in this business. Yeah.
Okay, thanks.
Thank you for the question. Okay, so maybe let me now, if there's no other questions, proceed to the next topic, which is, like I emphasized, how do we get, what is there anything in an effect? So let us imagine we have some effective field theory, which at low energies has a Einstein gravity, positive cosmological constants, and matter fields. Yeah? Is there any quantity that we can compute that is invariant under all of the gauge symmetries and the redefinitions of choices of field variables and so forth? Something akin to the S matrix, at least at the calculational level. And so I'd like to study a particular object that has these properties, which will force us to go to Euclidean signature. Now, Euclidean signature is something that is commonplace in quantum field theory, but in gravity, it's a little more delicate. And the motivation for going to Euclidean signature is due to important results in black hole thermodynamics physics. And also in the context of ADS-CFT, we have evidence that since CFTs make complete sense in Euclidean signature, there is, I think, an argument to be made that Euclidean gravity in ADS at least makes sense as well. So here we would consider Euclidean gravity, but for lambda positive. So, and we're going to take, so now we're studying Riemannian gravity with a lambda positive, and we have to find a maximally symmetric positive curvature space. And this is the sphere. Yeah, this is the Euclidean de Sitter world. And it's interesting to contrast the expanding space-time in Lorentzian signature to the completely closed universe. It's a closed manifold, the sphere. in Euclidean space time. And in order to get this, for instance, we can go from the static patch and weak rotate the time into a coordinate psi, which has to be periodically identified, which is reflecting some sort of thermal KMS type behavior of physics in the static patch. And the isometry group is no longer non-compact. It's just SO5, SOD plus 2. Yeah. And so this is the strange world, in a sense, of the positive lambda Euclidean gravity. It's a world where everything is compact and closed. So this is to be contrasted with the black hole case, where instead we have manifolds which have a boundary, and the boundary of the manifold has a structure of something like an S1 times S2, where the S1 is data that we have to specify, and that data corresponds to the temperature of the black hole in Euclidean signature. So here we don't have an analog of a tunable thermal cycle. It's just a closed manifold. This is one of the reasons that the de Sitter is different from the black hole. So based on this simple geometric observation, it was proposed by Gibbons and Hawking and others that maybe we should calculate the gravitational Euclidean path integral over closed manifolds. And so here, you should imagine as some general effective field theory action. Maybe it has higher derivative terms, whatever, it's some gravitational action. However, it's dominated with low energies by the Einstein term. And this could be some general matter fields. And although this is not a rigorously well-defined notion, in the sense of a saddle point approximation with loops, this makes sense. And so they suggested we compute this at least in the sense of the saddle point approximation. Okay, and then they didn't specify what closed manifolds we should sum over, but they did certainly suggest we should include this field. We will discuss other closed manifolds later in the talk. So the dominant saddle, which is the one that has the most negative on-shell action, is indeed the most symmetric, which is the round sphere. Yeah, and so we'll start with an analysis of the sphere. But before doing that, one interpretation is that this quantity S was observed in the old literature already, that to leading approximation, where you calculate the on-shell action on the four-sphere saddle, to leading approximation, X is given by this quantity over here, which is a rather beautiful quantity, 3 pi c cubed over lambda g h bar. It has all of the constants of nature and cosmology. And this quantity is the area of the de Sitter horizon divided by 4g. So this is reminiscent of the Beckett-Hawking relationship. And it has been speculated over many years that it's some sort of entropy or quantum information of cosmology. So this could be potentially a very physically interesting object to understand in more detail. This is sometimes called the de Sitter entropy. But we don't have a lot of evidence compared to black holes that this is an entropy. It's an interpretation of a calculation. And in our world, if we compute it for the measured value of lambda, this gives 10 to the 122. And so it's a different way of expressing the cosmological constant problem. Why is the de Sitter entropy so large in our world? Yeah. So let's go back and let's imagine that we find a saddle. And on top of this saddle, there's some weakly coupled matter fields that live to leading order. They perceive the world to be a force sphere, and we can path integrate over the matter fields and study their one loop contribution, for instance. And so for S equals 0 and S is equal to 1/2, or so spinless and spin-1/2 particles, we somewhat remarkably can express the partition function of the matter fields in terms of these Harish-Chandra characters in a way that looks as if it's a thermodynamic formula, even though there was no thermal cycle in the problem. But thanks to this density of states of Harish-Chandra's character, one can write the partition function in terms of Lorentzian information. So maybe I should emphasize that this is a Euclidean force field calculation that we are expressing in terms of Lorentzian characters of the de Sitter group. Yeah. And it's interesting formula because it takes an apparent thermodynamic behavior, even though there is really no rigid thermal cycle in the problem. Okay, so we have a new type of character formula for the partition function, and this is true for in an exact form for spin 1/2 and spin 0. And let me also tell you that when you increase the spin, the intrinsic spin of the particle, you get essentially a similar formula, except that the contribution from the character gets corrected by a rather interesting subleading effect, whose behavior is as if it was a codimension 2. It's living in 2 lower dimensions, which is the dimension of the horizon, a type of correction. And we suggested that this might be a type of edge effect associated to the de Sitter horizon. And it corrects the bulk contribution with a minus sign, actually, which it effectively removes a few degrees of freedom, which will play an important role later on. And so for higher spin fields, massive or massless, I should say, we get a corrected version of this type of character formula, which is corrected by these edge effects. And sometimes in the literature, from different means, people have calculated edge modes and the contribution to entanglement entropy from edge modes. And wherever they have computed it, and we could compare, they matched exactly. And in fact, we now have a prediction for the contribution to entanglement entropy for edge modes for arbitrary values of the spin in this context, which is including the graviton. And there was nice work actually studying this problem by Justin David and Jatirmo and Mukherjee some years ago. In addition, things like heat kernel coefficients are coded in a small t expansion, and similar character expressions also arise for gauge fields, except they have one additional term that's related to the gauge group volume. I'll show you in a second. So this formula is for massive higher spin fields. For gauge fields, you'll have this formula plus another term, which has to do with the residual gauge group volume. So let me show you, for instance, for 4D gravity, up to 1 loop, what it looks like. So the leading contribution comes from the on-shell saddle. We discussed that. The group volume contribution, which has to do with the fact that we have to divide by the diffeomorphism group, which includes the isometry group of the sphere itself, it turns out to contribute a logarithmic correction to S0. So it's actually a very dominant contribution. And then there's the bulk and edge split contribution to the logarithmic divergence. Right? So these are quantum field theory path integrals. So they have the logarithmic divergence that are regulated by some reference effective field theory cutoff scale. There is a scheme-dependent constant term. So here the scheme is the heat kernel. And there's a phase. The reason that there's a phase, which is also different from the black hole case, is that there are some additional zero modes in the path integration contour that have to be Wick rotated in order to be Gaussian suppressed. So this was initiated in work of Polchinski. Well, it goes back to Hawking, but clarified beautifully in work of Polchinski. And it is believed, and there's a lot of people trying to understand the nature of this phase, but it is believed that the phase is meaningful and not to be discarded. Yeah, so this is the one loop pure quantum gravity partition function, if you were ever curious about it. And indeed, you can restructure it in terms of bulk and edge characters. And the bulk character is written in terms of a unitary, irreducible representation of the discrete series of Harish-Chadlan. Okay, so the point, I guess, here is that even at one loop, and likely at higher loops also, there's a very physical way to express the rather featureless sphere path integral in terms of Lorentzian unitary group theoretic content. And it's remarkable also that it appears to capture properties, refined properties of entanglement, like edge versus bulk contributions, as well as rather universal types of corrections that any microscopic theory, candidate microscopic theory, should presumably match. Okay? Okay, so let me pause again and see if there's any questions, because yeah, we will move on to the next topic now. Okay, so just to recap, what we discussed so far was the geometry, the symmetries, the classification of matter fields in terms of unitary irreducible representations. And then we moved on to study the Euclidean path integral and the leading saddle point approximation as motivated by Black-Hole thermodynamics in conjunction by Lewis and Hawking. And we found that even though the sphere saddle itself is rather featureless and has no thermal cycle, at least at one loop, we can express arbitrary contributions from arbitrary matter fields in a form that is governed by Lorentzian unitary characters. Yep. Now, I would like to now make some comments about contributions that are subdominant compared to the sphere. And the reason that I'm interested in doing that is that, like I said, if we are to produce, we would like to produce an amount of invariant calculational data that is comparable to the amount of physical couplings that we expect the effective field theory to have. Now, the sphere is one saddle, and that's already interesting. However, it would be good to know whether there are many other saddles that code more physical information. And one thing I should have emphasized is that this path integral over here around any given saddle is indeed diffeomorphism invariant, gauge invariant, and locally field redefinition invariant. So the point to be made here, perhaps in addition to the point of Gibbons and Hawking and others, is that these path integrals around any given saddle satisfy the degree of invariance that we were discussing in the beginning of the talk. And so that remains true around the sphere, but also around other saddles. So having said that, I'll move to saddles that go beyond the sphere. So firstly, we'll consider the problem in the context of pure gravity, and then briefly mention adding Maxwell fields. So what we would like from a slightly mathematical way of expressing the problem is to find additional solutions to the Euclidean Einstein's equations with positive curvature, with constant Ricci scale. So these are objects that mathematicians study. These are Einstein metrics. And one would like to know what closed form manifolds there are that admit smooth positive curvature Einstein metrics on top of them. Okay, so this is the nature of the problem. Could someone send in the chat if you can still hear me? I'm a little worried that my connection is not very strong.
Anninos, I have one quick question.
Is there a question?
Yeah, so I have just one quick question. So this series that you have written, S4, CP2, S2 cross S2, and CP2, this thing K going to 1 to 8. So these are basically all the set of all the closed manifold in 4 dimension?
That are known. It's not a complete list.
Okay.
It's the known list. Yeah.
I see.
Indeed. Sorry. Thank you. I'll clarify that. So this is the currently known list of all manifolds. And on these manifolds, there's only a priori there could be multiple metrics, Einstein metrics on S4, but there's only one known. There's only one known, which is the round metric on S4. On CP2, there's only the Fubini-Studi metric known, so there's only one metric known. Similarly, on S2 times S2. And these manifolds over here are known as connected sums of two CP2 spaces. This bar indicates the opposite orientation, and K indicates that we've removed a number K points from the manifold at generic locations and glued them along these points after doing a procedure known as a blow up. And these are sometimes called Del Pezzo surfaces.
Okay.
And K is only allowed to take the range 1 all the way through to 8. However, when K is between 5 and 8, there is a full continuous moduli space of metrics that lives on these manifolds, which are physically distinct. So there is really an infinite number of saddles because of this moduli space, which is perhaps reassuring that we have enough, even in this known list, there's enough distinct data if we study the pattern rule around each of them to define in an invariant way each and all of the couplings of the effective field theory.
I see.
Moreover, the volume of these manifolds are known, and one finds a natural organization of the on-shell actions, if you will, dominated by the force field, followed by CP2 and so forth. And I think it's interesting to mention also that of all of these manifolds, only S4 and S2 times S2 admit spin structure. And the rest, which are orientable 4 manifolds, I should say, only admit a generalized version of the spin structure, known as the spin C structure. And we can only place particular particle spectra on these. For instance, we could ask whether we could place the standard model of these manifolds, which only admit a general spin spectrum. And the answer actually restricts what completions of the standard model we can place on them. For instance, in particular, the standard model can only be placed on these manifolds if we gauge the B minus L symmetry of the standard model, which is the non-anomalous global U1 symmetry. And so these very abstract questions, ironically, may lead to interesting phenomenological considerations, which I find satisfying. Okay. If these saddles contribute to the partition function that Gibbons and Hawking instructed us to compute, they will do so in a very particular way. It's the standard saddle point approximation. And you see that each of them will come with their own phase. It will be a very detailed type of formula. Each of them will have different logarithmic directions. And so one starts to see that this partition function, far from being featureless, can code a rather vast amount of invariant information inside of it. And so we have the possibility to define a more extensive invariant data set to define our theories. And moreover, I should also emphasize that all these saddles, except S4, if they contribute, lead to potential violations of the de Sitter symmetries, because none of them produce de Sitter invariant expressions as they break the de Sitter symmetry. So these could be violations of the de Sitter isometry. Yeah, and that would be an interesting problem to further understand, whether we have to break in the end, ultimately, in whatever the fundamental description of this theory, the de Sitter isometries are only an approximate notion in some semi-classical regime. Yeah. So to push the point a little further, and to show you how gravity is different from quantum field theory, let me give you the following. So in quantum field theory, where we could study some partition function in a sphere, one often has ultraviolet divergence. In 4 dimensions, you would have a UV divergence that renormalizes the cosmological constant, Newton constant, and another one that renormalizes some Gauss-Bonnet coupling constant or some R-squared coupling constant. And you say that these are ambiguities of the partition function. In theories of gravity, since these are physical constants that we have to renormalize, we shouldn't really say that these are ambiguities, but rather that we have to measure a few more couplings in order to render this object meaningful. But I would like to add to that if we have multiple saddles in the theory, we can take linear combinations of their contributions and produce quantities that are completely insensitive to this UV cutoff parameter epsilon, right? So if you just have 3 saddles in 4 dimensions, you can start taking different linear combinations and ending up with what appears to be a truly invariant quantity in the quantum theory. And so this goes to show that unlike quantum field theory, when you have gravity coupled to quantum field theory, you can have more invariant information content. And finally, for this section, let me make one more point. And the point here that I'd like to make is that, of course, we don't expect the theory to be just pure gravity. And if we add additional fields, as a simple example, the Maxwell field, we will have many more couplings in the effective field theory, because we'll have f squared, f to the fourth, to the sixth, and so on. And so this reasoning might lead us to expect that there's new saddles in the equations. But this is in fact the case. So the Einstein-Maxwell theory admits an infinite novel class of non-Einstein instantons that were not present in the pure Einstein theory. For instance, products of closed Riemann homogeneous surfaces times a two-sphere. Okay, and so we have new saddles that may account for new physical couplings in effective field. Okay, so let me pause again and see if there's any more questions at this stage.
Anninos, in this slide where you showed the UV divergences.
Yeah.
So as I understand, you're saying like there is probably like some linear combination of various manifolds so that the UV divergence won't be appearing then.
Yeah.
So, suppose we cancel the leading divergence, then basically that same linear combination will cancel the other divergences also, or like for each of them, like we'll have to do order by order some arrangement.
Well, so there's a finite number of UV divergences that appear. So here I'm taking epsilon to 0, and we don't consider the other terms as divergences because they vanish in the continuum limit. And so what we would like, so if the question mathematically, I guess, is if we have these three functions of epsilon, is there some combination of them that is independent of epsilon?
Right.
And I'm saying that if we have enough such structures, we can take linear combinations that start to remove all the dependence on epsilon.
Okay.
I mean, there could be degeneracies that don't allow three saddles to do it, but we have more saddles in principle. And I guess the other point to make is that these are okay. So I reported on the one loop expression for S4. So maybe you're asking about higher loops.
Yeah.
Of course. So in higher loops, we will have to confront. It's a non-renormalizable theory. We will have to confront the renormalization of other couplings as well. Yeah. And we will have to deal with these new divergences, and that's why it's important to have more and more saddles. Yeah. So that indeed. So here I was just making this simplistic point at the level of one loop where we only have this type of quantities appearing.
Okay.
Yeah, in general, we will have to do this for a much more elaborate problem where we should really assume that we have an effective field theory with all the R squared corrections, R to the fourth corrections. And then we would probably have to consider a rather large list.
Right.
Of saddles with their expansions.
But even at the level, like, can it be arranged? Like, the first three terms are the ones which are the leading divergences in the one loop level. So the first is this epsilon 4, epsilon square, and this 1 over epsilon. So like even at this one loop level, so the numbers are such that I'm not sure whether if that can be cancelled, all of them. So suppose we cancel 1 over epsilon 4 by making some arrangement. Maybe 1 over epsilon square can be also cancelled, but I am not so sure about 1 over epsilon 1. So this log divergence one.
So 1 over epsilon doesn't. You're asking whether there should be a 1 over epsilon term?
No. Sorry. I read it wrong. So it is a log epsilon term. So this is this log of 1 over
log epsilon.
Yeah, log epsilon.
Yeah, log epsilon. Log epsilon.
Yeah.
And I should say there's no 1 over epsilon cubed and 1 over epsilon because these are not related by the locality of the field.
That's true.
Yeah.
So 1 over epsilon 4 can be cancelled by making some arrangement, and 1 over epsilon square will be also cancelled. But how about these log epsilon terms? They can be also arranged to be cancelled by the same arrangement.
Well, yeah, and if not by these three, certainly by if you have additional ones.
Okay,
Yeah.
I see.
It's just, I just want to make the point that this a sufficient number of such one loop expansions, barring degeneracies, will lead to cancellation.
Okay.
Yeah, at the one loop level.
Yeah.
It's yeah. I think it's an important point to make because this is inherently non-quantum field theory reasoning.
Yeah.
In quantum field theory, we don't sum over different geometries, and so these kind of possibilities are not present. Yeah.
I think there are a couple of hand raised and maybe.
Hello? Yeah, I have a quick question. When you were considering the saddles and the geometries, so you like the list of the geometries that you showed, like S2 cross S2 and other things, there you were not considering any genus corrections, right? But later, you commented that there can be contributions coming from genus correction.
Yeah, indeed. So here I was thinking of a theory that was pure gravity. And it's an interesting feature that none of the manifolds that admit Einstein metrics, so solutions to pure Euclidean gravity, have, for instance, non-trivial one cycles. Okay. It is simply, in fact, I believe that might even be a mathematical result, that positive curvature Einstein metrics cannot admit non-trivial one cycles. Of course, CP2 and S2 times S2 have non-trivial two cycles. Yeah. So they have non-trivial, and as do these over here. And so you can have non-trivial two cycles, non-trivial four cycles, but you can't have non-trivial one cycle. In order to get these higher genus type of terms, we had to change our equations of motion to the Einstein-Maxwell lambda equations. And these solutions are not Einstein metrics. They only solve the Einstein-Maxwell equations with non-trivial Maxwell contribution. So they will also have electric fields and fluxes. And then we can understand these solutions. For instance, in Lorentzian signature, you could have something like a magnetically charged black hole in the center space. Yeah. And you could make it an extremal magnetically charged black hole. Then in the near horizon limit, you will have an ADS2 times S2 solution to the equations of motion, even with lambda positive, which in Euclidean signature becomes a two-dimensional hyperbolic space times S2 with magnetic flux piercing through the two sphere. And you can quotient the H2 into an arbitrary genus Riemann surface. And so you find new compact manifolds in Einstein-Maxwell lambda theory that were not present in the pure Einstein theory because there was no magnetic field that I could turn on previously. Okay. Does that answer the question?
Yeah, and could you comment on this Nari limit? So there, do you need that genus correction? Because I guess that will be a black hole, charged black hole.
Nari can be indeed either a charged black hole, but it can also be neutral. So the simplest Nari black hole in Euclidean signature is just S2 times S2.
Okay.
Yeah, but we should go between Lorentzian and Euclidean in a little more delicately because not every Euclidean instanton has a direct Lorentzian interpretation.
I see.
Right. So their role in life is to contribute to the partition function, and then we have to see what it is, how they contribute to the partition function, and then perhaps the partition function has a Lorentzian meaning upon adding them all together. So we should be a little bit cautious about pushing a Lorentzian interpretation too quickly.
Okay.
I think what is important to me is to understand how big the list of these solutions are, and along the lines of the previous discussion, how much information they can encode. How many can I define, for instance, the coupling of Wild square, the Wild squared higher derivative term in some linear combination of these saddles and their loops. Because this might be ultimately the way that the information is coded in this theory in the absence of an S-matrix. Perhaps if it's useful for some of you, it might be a little more reminiscent to things like topological quantum field theory, which are theories that don't really have an S matrix or local operators, but there's a lot of rich physical quantum information coded in abstract things like Euclidean path interference. I don't know if that's a helpful analogy. Okay, so maybe let me move on to
There is one more raised hand by Pradipto.
Oh, sorry. Yeah, please.
You are only concerned about the one loop corrections, right? On top of
I'm concerned about all loop corrections. So far, there are robust results at one loop, and I think it is a very interesting question to go beyond one loop.
Okay.
If I had more time, I would tell you about higher loop corrections in 2 and 3 space-time dimensions where I have a better understanding. But I don't have a complete understanding of higher loop corrections, even 2 loop corrections in 4 space-time dimensions. This is an ongoing problem that I think people should study.
Okay, thank you.
Yes. Okay, so now I'll move on to the last point that I'd like to make, which is motivated by the following question. Imagine that someone comes and tells us that they have a complete list of particles in a theory that has lambda positive, and that this particle spectrum is perturbative. So this is a little similar to someone coming and telling us that they knew a complete list of particles in 26-dimensional Minkowski space, and that it's a perturbative spectrum. And imagine that that's the information we had, and that we could compute the one loop contributions to the partition function of this particle spectrum. So what would happen if this spectrum was string theory? In string theory, what would happen is that we would add up the one loop contribution of the free energies of all these particles, and we would get a result that looks a lot like the genus 1 contribution of a worldsheet theory. Yeah. In other words, it's a nice exercise to reinterpret the genus 1 contribution of the worldsheet theory, of string theory, in terms of a target space quantum field theory calculation. And what it is a sum over an infinite number of one loop target space contribution. Similarly here, I think it's interesting to ask, even at one loop, notice that everything in the string theory context, as I said, was a one loop problem. At one loop, we could ask, if we have someone complete particle spectrum, does something happen when we add them all up? Now, we don't have complete theories of quantum gravity in de Sitter, but there is one particular model that I think is worth studying, which is a model where you have an infinite tower of massless higher spin gauge fields, because these make sense in de Sitter as well. And we could ask what happens if we sum together a spectrum of particles. And here I'll give you a particular example where we have a conformally coupled scalar in de Sitter 4D de Sitter, plus an infinite tower of even massless gauge fields. So the graviton spin 2, spin 4, spin 6, and so forth. So given our one loop results, I would like to sum up the 4-sphere one loop contribution of this infinite tower of particles. Okay, so this is a type of particle spectroscopic question that we could ask. Yeah. And so I've written what the sum would be in terms of these characters. So this over here is the character of a complementary series that delta is equal to 1. That's this conformally coupled scalar. And these over here are the bulk and edge contributions of these higher spin gauge fields. And we're going to sum everything up together. And note that each term in this sum has the type of divergence that we discussed before. There's the epsilon fourth, epsilon squared, and log epsilon. Yeah. Interestingly, when we do this sum over all of these particles, firstly, it's interesting that the sum can be done at all. And secondly, because, like I said before, the edge modes contribute with a negative sign, yeah, one can end up with a very different looking answer than any contribution within the sum. For this particular example, the output of this infinite sum are 2 identifiable contributions, each of which, instead of having 1 over epsilon to the 4th, 1 over epsilon squared log epsilon, has 1 over epsilon cubed, no log epsilon, and 1 over epsilon. So these have the divergence structure of a 3D theory, even though our calculation was on a 4-sphere, and there was no 3D anything. Yeah. So this is a rather interesting situation. There's still divergences. However, the nature of the UV divergences is different. Now, let me tell you in a little more detail what these two pieces are. So the resulting pieces have actually appeared previously in the literature in two separate contexts. So the first piece has appeared as the one-loop partition function of a very curious theory, which is a 3D conformal higher spin gauge theory defined in a three-sphere topology that various people have studied. And it looks precisely like this. So it's as if the output of this infinite sum was the one-loop character of a three-dimensional conformal higher spin gauge theory. And because it's a 3D type of theory, the one-loop contribution, even though it has many fields, is very simple. And the second piece is twice, this is this factor of 2, the partition function of a free conformally coupled scalar field on S3. Yeah? So these two terms are not just abstract, they appear to be related to a conformal high spin gauge theory and a free scalar on S3. Okay? And so one is inspired at this point to try to understand whether this one loop structure could be the result of some large N approximation. And I think one possibility is that what's happening is that these two terms are appearing from some type of a path integral over conformal higher spin gauge fields of a CFD partition function, some sort of ON model, where we've turned on sources for each of the ON invariant currents. This B represents the space of sources for all the currents and scalar in the free ON model. And we're squaring this. So this is this factor of 2 over here, I'm imagining. And my claim is that the large N limit of this theory is a perturbative theory in the conformal higher spin gauge fields, which at one loop will agree with this object over here. In other words, the one loop sum that we made seems to suggest that there is a way to understand the force sphere path integral of this theory with all these 4D higher spin gauge fields in terms of some sort of gluing of two theories that live on an S3, a common S3, where conformal higher spin gauge fields are path integrated over. And what I like about this possibility is that even though the force sphere is itself featureless, it might be that its more microscopic or fundamental definition may require the introduction of some hypersurface inside of it that we have to glue together in order to make sense of it. Yeah. So this is a type of formula that we might land on from considerations of perturbative particle spectra. And to leading order in N, we can calculate the leading contribution, and it's a large positive number, as we may anticipate if this is an entropy. And one can systematically compute one over N corrections, which is a problem I'm studying with these authors and Beatrix Mullman also. So perhaps this is a type of gluing formula, and I'm quite intrigued by this formula. So, okay. So I think, yeah, let me end just by concluding that I think we are at a phase in this problem where we need the sharp and concrete calculables at the quantum level to start clearing up the interesting quantities, such as S, or physical quantities or invariant quantities, or maybe because of these phases or whatnot, they will lead to concrete inconsistencies. But I think we have to collect a systematic and large theoretical data set for this problem that is as precise as possible in order to proceed in as educated a way as we can. So thank you for your time.
Thank you, Ninos, for the nice talk. And now we are open for the questions. So if people want to ask.
Okay, I'll try to put my video on again. I don't know if it will collapse everything, but.
Let's see if there are any further questions. I don't see any raised hands any further. Arnab has a raised hand.
Yeah, thanks for the nice talk. You showed some connection at the level of partition function, But could there be some other quantity, for example, some correlation function which has some analog to some ON model correlation function?
So yeah, so it's interesting to consider correlation function, but if I insist on the degree of invariance that I wanted, I would like this correlation function to be diffeomorphism invariant and field redefinition invariant, and so I would have to find something like the analog of the LSZ reduction formula that would map these correlators to something physical. And so that part is the thorny part, particularly if I restrict myself to correlation functions within the physical region of the spacetime, which is the static type. And so what people have tried to do in that context is add some extraneous feature, like a little tube or whirl line, and try to relate observables to that feature. But then the answer becomes sensitive to the details of this feature because it's externally placed. And so that's the state of the art, I think, in terms of that question.
So am I right to understand that when you say details of that structure, so that is the rigid space-time structure that we are considering, not the quantum corrections of other topologies?
So anything I said, so first of all, the space-time is not rigid even at the level of the sphere topology because we're path integrating over the metrics. And so so it's a wobbly sphere, if you will. So space-time is really not rigid throughout this talk because we're allowing fluctuations.
No, I meant the comment that you just made, regarding this correlation function. When in that geometry, when you compute some correlation function, that will depend on the details of the geometry. So this geometry refers to this. What I meant is that does this geometry refer to this particular metric that is there on slide, or does that also?
The problem is that the metric itself is fluctuating, and so when you try to compute a correlation function, you have to tell me what you mean by the points along that you're labeling the correlation function with respect to in a dynamical metric. So you have to define maybe 2 points that are separated by a proper length that is fixed, and then the endpoints have to be fixed by some other relational notion. It's not easy to construct.
Right. Okay.
Truly invariant correlators. Now, in de Sitter space, and because of course, we have an asymptotic boundary where we switch off the dynamics of the metric, and we have a reference frame, which is the asymptotic boundary that we can describe physics in the interior with respect to, and this is how we get away with it. But in the absence of this reference frame, it's much harder to proceed.
Any other questions? So if not, then let's thank the speaker again for the wonderful talk and agreeing to give a talk in this seminar series. And thank you, Anninos, for the nice talk. And
thank you. Yeah, and the best of luck with your seminar series. I hope it's very successful.
Yes. Thanks.
Okay.
Okay. Bye.
Take care, everyone.